You're actually filming this right now?
Mm-hmm.
Good afternoon. Welcome to Business Statistics Session 7. We've made it to the last class. Congratulations. Really proud of you. I got nothing. Hey guys, welcome back. Glad to have you here. We made it to session 7, as you can see, and unfortunately that means we're coming to a close, coming to an end. This is the last class. If you've made it this far, congratulations. I hope I've taught you well. Let's get started. So, last week we talked about a one sample hypothesis test. So this week, obviously, we're going to talk about a two sample hypothesis tests. Okay? All it really is just comparing the two sample estimates with each other. And that's it. And basically same thing about testing the null hypothesis against the alternative. Okay. Again, one sample test, it deals with comparing a sample estimate with a non-sample benchmark, right? So you just replace this non-sample benchmark with a second sample, and then you compare the two. That's kind of the difference. I just kind of put some examples like where they show up. Crash test comparisons, right? You take one sample of crashes. Obviously test crashes, not real crashes, I would hope. Maybe, I don't know. Marketing, when comparing sales, environmental analysis of two manufacturers. If you're testing their methane gas emissions, safety analyses, there's so many others. This is just to name a few. Just real world applications for you, so that way you can never say, I'm never going to use this in the real world. Well, yes, you are. You're wrong. Okay, the basis of two sample tests. They're pretty much useful because it has a built-in point of comparison, right? If I'm testing old versus new, before versus after, experimental versus control. Just kind of quickly, that's kind of what it just helps compare things, right? That's what I talked about earlier. Test procedure. Again, same thing as our one sample hypothesis test, right? We have all of our steps that we do. We state the hypothesis, set up our decision rule, insert the sample statistics, find the sample statistics, and then we make our decision and take action. I didn't put take action in here because normally, like we talked about, that's somebody else's job. So as you can see, we have our 3 different tests here, right? We have our left-tailed test, two-tailed test, right-tailed test. Again, you can always tell the direction of the test by these symbols here, right? So right-tailed test, obviously think of it as like an arrow. It's pointing to the right, therefore you got to do a right-tailed test. This one's pointing to the left. And if this is not equal to, just imagine anything not equal to this, right? So just in both directions, it can go both directions, all right? Again, it's denoted as mean 1 minus mean 2. In two sample, that's how we denote this, right? We have to do mean 1 minus mean 2. In a one sample test, it's just mean 1, right? It's just this simple one here. Okay, so this is just real simple. This is when we state the hypothesis, okay? Test statistic. Our sample statistic we use to test the parameter, again, is mean 1 minus mean 2, which is basically just saying X bar. So your sample mean, this is probably like our population mean, probably like our test, I guess what we're testing against, sort of. In this case, it's just saying this is our sample, first sample mean minus our second sample mean. They're both calculated from independent random samples, again, that we take from the normal populations, right? And we follow the same general format as the Z and T scores we calculated earlier, okay? And there are 3 cases to consider when doing these two sample hypothesis tests. And the first one we're going to talk about is when we know the variance, right? When we know sigma squared, okay? There's always these different types of rules and situations that we have to account for and figure out which formula to use. And in this case, if we know the variance, if we know sigma squared, we'll use this one, okay? And so this is just our Z statistic. So if we need to find the Z score of our test, this is the formula we use, right? And just some assumptions we have to make. The samples are random and independent, and they're drawn from normal distributions, okay? And then the population variances are known. Again, it tells you here. Again, so this is our formula, our z-score, and we just take the sample mean minus the first sample mean minus the second sample mean, subtracted by mean 1 minus mean 2. And again, we'll go over this. This is just the magnitude, right? This is that this is that d sub 0 that we talked about. It's just subtracting from d minus 0, okay? That's all that's saying. And then you put all of that over the square root of your variance over the sample size of your first sample, add that to the variance of your second sample, divide that over by the number of your second sample, okay? I know that was really wordy, but this is a lot cleaner, okay? It just makes sense, right? A lot of it's just plug and play, guys. Don't have to worry about it, just plug and play, and then algebraically figure it out based on the order of operations, okay? PEMDAS. All right, case number 2. When we don't know the variance, but we're assumed that the variance, the two sample variances are equal, right? So we don't know this, but we can safely assume that this right here is equal in the two samples, right? So what we do is, when they're assumed equal, we have what's called a pooled variance. So we pool those two variances together. And this is the formula for that, okay? So we have our sample size minus 1 of the first sample times and this is our sample standard deviation, right? So we have our first sample standard deviation squared. Same thing over here, second sample size minus 1, our second sample standard deviation squared. And then we take all that over n minus 1 plus n minus 1. Okay, and this is our first sample and second sample. All right, so once we get that, we bring it down here and we plug it in right here, okay? So again, it's kind of the same thing up top, right? Our sample mean, first sample mean minus our second sample mean, minus the magnitude, all of that over this, times this, okay? And it's not that bad. Again, plug and play a lot of times, guys. It's really not hard. And again, we're taking a t-statistic here, so we have to find the degrees of freedom. We find the degrees of freedom here by n1 plus n2 minus 2, right? So our sample size from the first sample added to the sample size of our second sample subtracted by 2, right? And if you think about it, it's just the same as a degree of freedom. It's the same as a one sample hypothesis test, but again, n minus 1 is the degree of freedom there. You have to do it twice, therefore minus 2. Okay, makes sense, logic. So this is the formula we use when variance is unknown but assumed equal, okay? So the third case, obviously, it's probably going to be sigma or variance unknown, and then but it's also assumed unequal, okay? This one isn't as bulky as this one is. It's a lot easier, okay? If it's not known, or if it's assumed unequal, so if this is different between the two samples, our t-score, again, we have to do a t-score, is sample mean 1 minus sample mean 2 minus the magnitude, all of that over our first sample standard deviation, or I guess our variance in this case, because it's squared. That's important. And we add that to our, over the first sample size, and then we add that to all of that in the second sample, okay? Again, this is where reading the word problem comes in handy, okay? Because a lot of times it'll tell you, you read it left to right, and it'll usually go in order, right? So they'll give you all of the information, you write it down, what's your first sample mean, second sample mean, what's your sample variance from the population 1, what's your sample variance from population 2, and then they'll probably tell you a lot of times, if it's assumed unequal or if it's assumed equal, okay? They'll normally tell you, all right? If not, you can just kind of look at it, and if they're not really that similar, if these have like a very wide range between the two, they're probably assumed unequal. That's just, again, logic, common sense thinking, okay? I think, and the degrees of freedom for this is really ugly. I don't like it. It's called the Welch's approximation, and Welch is obviously not a fun person to deal with. It doesn't look like, he didn't seem like a fun guy to be around, because that's ugly, all right? So instead of making you find the degrees of freedom, again, this is just for, I just want to make sure, finding the degrees of freedom, like for Welch's approximation, that just deals with case 3, all right? Shoot, I hit the wrong button. Sorry, guys. That's just for case 3, okay? But instead of doing all of this, it's gross and ugly and I don't like looking at it, okay? What we can do is just take the smaller of these two, right? So N1 minus 1 and N2 minus 1, whichever one of these is smaller, take that degree of freedom, okay? That's, it's a much more conservative approach, but it's definitely a lot easier on you, okay? So do it this way, don't do it that way. And I just decided, hey, let's do an example together to kind of make it a little bit less like Greek, so that way you understand a little bit better, okay? So, again, word problems are important. Always read them carefully. Underline the information you're given, write it down, figure it out, and then it makes it so much easier, again, it makes it so much easier just to plug and play into your equations, okay? So, the price of prescription drugs, and I guess I should have been and, sorry guys. Not good at typing. That's why I'm a math person. So the price of prescription drugs in an ongoing issue, or is an ongoing, oh, I just flipped these. Sorry guys, it's late tonight, sorry. Okay, let's try this again, third time. The price of prescription drugs is an ongoing issue in the United States. Zocor, which is a drug, is a common prescription cholesterol-reducing drug prescribed for people who are at risk for heart disease. We took samples from Colorado and Texas and wanted to see if there's a difference in the mean prices for all pharmacies in these states. And again, it gives us an alpha at 0.05, okay? And again, the word problem didn't give us all, I think it gave you all of these, but I just decided to break it all out for you anyway. It just gave you the sample means, the sample variance, the sample standard deviation, and then the sample sizes, okay? So I just wrote all these down for you. Again, in the problem, they'll be there. Just write them down. It makes it easier, okay? So, step one. Again, we're going through these steps, all right? So what's the first step we always state, or always do, is we state the hypothesis, okay? So in this case, we're trying to find, the question was, we want to see if there's a difference in the mean prices for all pharmacies in these states, okay? So if there's a difference, that means that it could be either on the left side or the right side, right? It didn't give us a specific less than, greater than, all that stuff, right? So in this case, our null hypothesis would be mean 1 minus mean 2 is equal to 0, okay? Our alternative hypothesis is mean 1 minus mean 2 not equal to 0, right? That means two-tailed test, we want to find it on either side, right? We have a rejection region on the left and a rejection region on the right, okay? So step two, we did step one, state the hypothesis. Step two is we specify the decision rule, okay? How do we know if we need to reject the null hypothesis? Well, this is what this is, right? So step two is we can assume an equal variance. It told me that in the problem. So it obviously didn't tell you in the way I wrote it down, but we're assuming equal variance here, okay? Trust me. And again, if we assume equal variance, that means we have a case 2 scenario, right? So we're going to use that formula. So for the pooled variance t-test, the degrees of freedom are, and again, we do n1 plus n2 minus 2, so 16 plus 13 minus 2 is equal to 27. So 27 is our degrees of freedom, all right? We all know the degree of freedom table is Appendix D, and we get the two-tailed critical value, t equal to plus or minus 2.052. And again, this doesn't deal with this, but just remember that alpha is at 0.05. That's important, okay? Because you have to, I guess in order to find this t-score, you have to know what alpha is, always, all right? Or you have to always constantly refer back to alpha, okay? So our decision rule is we can reject the null hypothesis if t is less than negative 2.052 or t is greater than 2.052, positive, okay? Otherwise, we can fail to reject the null hypothesis, okay? Pretty simple, right? All we've done so far is write a couple hypotheses down, find the t-score based on alpha using our appendix from the back of the textbook, okay? And then we write down our decision rule, okay? Now we get to go into step 3, which is where we calculate the test statistic, okay? And again, since the variance is assumed equal, we use case 2. All right. Again, I wrote all these down for you here. So step one, we have to find the pooled variance. Okay, that's important. We can't find this without finding the pooled variance first. Okay, so step one is we find the pooled variance, right? So we plug in N1 here. So 16 minus 1 is 15. You have your sample standard deviation. Square it, right? Do the same thing over here with your second sample. And then you divide all that. 16 minus 1 plus 13 minus 1. Okay, so 15 plus 12. And then you add those together, divide it. And I'm not going to do the math for you because y'all should be able to do that, hopefully. If not, text me and I will help you. Okay? But just think, PEMDAS was it, please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, from left to right, obviously, so if multiplication's first, you do it. So left to right, and then addition, subtraction. Okay? Again, left to right in the order. So, algebraically, you work all this out, you get that equal to 138.6737. Okay, so that's our pooled variance right there. It's pretty big, but it's gonna be fine. Okay, so we have our pooled variance here. Step two, we calculate the test statistic. So we plug this in for this variable here. So 138.6737 goes here. We take x bar, first sample mean, so 133.94. We subtract it by 138.018. And again, minus our magnitude, so mean one minus mean two. If you go back to step one, our magnitude was 0. Okay, so in this case, it would be 133.994 minus 138.018 minus 0. Again, because our magnitude was 0. That's all I have to say about that. Okay, so that's what that means, right? Anytime. Whatever this is, that's what goes in mean 1 minus mean 2 for the true population, okay? All right, so we put all of our numbers in here. We get negative 0.915. That's our t-score, right? That's our t-test statistic, all right? So what does that mean? We make our decision, right? Our test statistic, our t-calculation was negative 0.915. Again, that doesn't fall in the rejection region because it needed to be less than negative 2.052 or greater than positive 2.52. That's obviously not less than negative 2.052, and it's between this range here. So we can't reject the null hypothesis. We fail to reject it. So we can't reject the null hypothesis of equal means, right? So take action. What does it mean to take action, right? So since the difference in sample means is within the realm of chance, assuming null hypothesis is true, no further investigation is needed, no actions needed to be taken, we're good to go, right? We've done our job. Congratulations. That is our step-by-step look into the life of a two-sample hypothesis test, right? So now what we're going to do is you guys get to do these two-sample hypothesis tests yourself. Okay, so I just want you guys to do 10.3 and 10.5, but only do A. Okay, I don't want you to do B. I think B is making you guys do it in Excel, and I don't want to do it in Excel. And I think this 5-step process is a lot simpler than some of you may think. Okay, so do A, and then we'll get back and continue on here in just a minute. See you guys in a second. Okay, so again, we've done two sample hypothesis tests. Even in the last week, we talked about the 3 different ways to do the one sample test. We had the critical value method, which is the method we just got done learning for 2 sample. We have the p-value method, and then we have what's called the confidence interval method, of course. And so we're going to learn the confidence interval method for 2 sample tests, okay? Again, we already know what a confidence interval is, I hope, and we all know how to calculate it, right? And the way we test these 2 sample hypothesis tests, right, is if the confidence interval for the difference of the 2 means includes 0, we can conclude that there's no significant difference, which means we failed to reject the null hypothesis, right? So anytime that interval contains 0, we can't reject the null hypothesis, all right? All right, so sticking in the vein of case 2, okay, we're gonna find the confidence interval for 2 sample hypothesis tests when we assume equal variances, okay? So in any case, again, this is important, this pooled variance here, we have to figure this out first. Again, you'll probably have already figured this out. If you do, if you get to step 3 and then you're just like, oh, I don't really want to test it against the alpha, then you can just find the confidence interval. But you have to find the pooled variance first, okay? And then you plug it into this formula here, okay? And again, this is just for case 2. This is just for assuming equal variances, okay? So we take our first sample mean, we subtract it by our second sample mean, and then we add and subtract. So we have to add and subtract this portion here again, so we can get our interval, okay, our range. And then we have our t-score that we found. We multiply it by our SP. And again, this is important here. I put arrows. This is squared. This is not. So what does that mean? That means that once you get this, you have to square root it. Okay, so to get rid of this square, you got to square root the pooled variance to get your standard deviation, okay? Your pooled standard deviation. All right, so this is important. You can't put your pooled variance here and get the correct interval. You're going to get it incorrect, okay? So this is important. This is the square root, or this is the square root of that. Important. I can't stress that enough, okay? And then all of that is multiplied by 1 over n1 plus 1 over n2, and you square root that. All right? Clear as mud, I hope. So this is just for case 2, right? Case 1, again, we're not going to go over it in the slide, but if you wanted to, it's this thing plus or minus your z-score times, let me just go back to the first case. Again, it would just be x1 minus x2 plus or minus your z-score times this whole bottom portion here. Okay, that's all your interval would be for case 1, okay? I'm not going to go over it just because I hope it's pretty obvious. But again, case 3. Okay, we talked about case 1, case 2. This is for case 3. Okay, again, it's a little bit, to me, it's a little bit easier because you're assuming that they're unequal and you don't have to find their pooled variance or anything like that, and then square root it and all that stuff. To me, this is a lot simpler because all you're doing is taking the sample mean from your first sample, subtracting it from your second sample mean, add, subtract your t-score, then you times the t-score by the square root of your sample variance, or your first sample variance over your first sample size, add the second variance over your second sample size, okay? And again, we have this really nasty degree of freedom here, Welch's approximation. He approximately did not figure out how hard this is going to be. So instead of doing it his way, we're going to take, again, the minimum of our 2 samples, right? N minus 1, just the smaller of the 2, okay? So that's how we find our degrees of freedom for that, all right? So that's how we find the confidence interval for case 3, right? This is just for case 3. They each have different formulas for these. I'm really sorry, I know it's a lot, but it'll be okay because I have a surprise for you at the end of this that's going to make everything so much easier for you guys. You're going to love me, okay? So, an example for a confidence interval, okay? Again, this is coming straight out of the textbook, so if you guys are like, I don't get it, it's in the textbook, don't worry, okay? And this is a really lengthy one, I know, but bear with me, okay? So, this is kind of a real world example too. So, do teams that collaborate virtually feel they get along better than teams that collaborate face-to-face? I know that's an important question. At work, I deal with people face-to-face, but the majority of people I deal with are virtual, online, over the phone, Skype, Microsoft Teams, whatever it is, okay? So, this is actually a pretty cool question to pose. So, a study was conducted with senior marketing majors at a large business school, and students were randomly assigned to a team that collaborated online or a team that collaborated face-to-face, right? So this basically split teams up. One communicated virtually, one communicated face-to-face. Both teams were given 5 cases to analyze, and at the end of the study, each team member was asked to rate how well they felt their team got along by responding to the statement, "I felt our teammates got along well together." And then the response scale was a 1 through 5 Likert scale. It's just a Likert scale is literally just when you take a survey and they ask you a question or give you a statement and you have to say, I strongly disagree with that or I strongly agree with that. That's a Likert scale, okay? I know we've all taken them before, okay? So I I wrote down all of our sample mean, sample standard deviation, sample size, all that stuff. So we have all of our data. Now it's time to find our interval and all that, okay? So in this case, the population variances are unknown, but they're assumed equal. And again, note the similar standard deviations. If I go back a slide, you can notice that our first sample standard deviation is 0.76. Our second standard deviation is 0.82. I would consider that pretty similar, okay? So we want to assume that they're equal. All right, so that means we can use case 2, which unfortunately means we have to find the pooled variance, which we would then square to find S sub P, okay? So for a confidence level of 90%, we use the student's t-table. Again, degree of freedom, we do 44, N1 plus N2 minus 2, okay? We get 84. And then from appendix D, we obtain a t-value, or a t-score from alpha. Again, this is 90% level, so that means 10%, alpha is 0.10. We have to do alpha divided by 2, that helps us get 0.05, okay? And again, we get our t-score using 1.6, or equal to 1.664. And this is using 80 degrees of freedom too, by the way, because remember, when the higher the degrees of freedom get, they kind of do intervals of 5 to 10. So in this case, we always round down, right? Degrees of freedom, we always round down to the next lowest whole number that's on the table, okay? So we get our confidence level. We do x1, x bar 1 minus x bar 2. So we take x1, so 3.58 minus 2.93. That gives us this. We get our t-score here of 1.664. Okay, that goes here. And then we have our formula for the pooled variance. It's simple plug and play here, right? We have all of this information. It's just as simple as plugging it in and figuring it out, okay? If you have a calculator, you can figure it out, I promise. But you could also do it by hand and it would not be hard, I promise, okay? So we figure that out, and then once we figure this out, we take the square root of it, put it here, and then we take the square root of 1 over n1 plus 1 over n2, multiply all that together, plus or minus that, we get 0.65 plus or minus 0.284, or we get 0.366 and 0.934. So this is our interval, okay? And again, remember what I said, if the confidence interval does obtain 0, we fail to reject the null hypothesis. That's really close to 0, but it's not 0, okay? So 0 is not in our confidence interval. So we can say that with 90% confidence that there is a difference between the means, right? So we reject the null hypothesis, okay? That's all that this is saying. This is the confidence interval way. Again, case 2, confidence interval for case 2 is probably a little bit more cumbersome than case 1 or case 3. So I would always use probably the critical value method for case 2, but case 3 definitely would be an easy calculation for confidence interval if you want to do it that way, okay? But to each his own, pick your poison, whatever you want to do, however the saying goes. Another pun, okay? So, it's problem time, okay? I'm just giving you one problem to do, right? I want you to do 10.10a and 10.10b. That's all I want you to do, okay? And then we will reconvene after y'all are done, and we'll get going some more, okay? See you guys in a second. Welcome back. All right, guys. We're done with 2 sample hypothesis tests. You can take a sigh of relief. But we have one more thing to cover in this class, and then you're done forever, okay? Until next week when you have to take the final. The last thing we're going to learn is what's called a chi-square test, okay? And again, this is just because the reason these were kind of invented is just because not all information can be summarized numerically, all right? This is also just pertaining to business and stuff like that. So they often ask, like, do employees in different age groups choose different types of health plans? That's a question to ask. It's a really important question to ask. Do consumers prefer red, yellow, or blue package lettering on our bread bags? I don't know if that's actually important or significant, but I'm sure there's a bread company out there who thinks that this is an important question because, let's face it, everyone loves bread. My wife especially, okay? So, another question to ask is, does the name of our new lawnmower influence how we perceive the quality, right? I guess names are important in lawnmowers, okay? John Deere, just the only lawnmower I can think of, okay? So, just questions like that, that's how we can these kinds of tests is how we can kind of gauge whether or not there's a significance to these, okay? So, we can collect observations on these variables to answer these types of questions by surveying the customers or by well-conducted experiments, and we put them in what's called a contingency table. And I hope you're familiar with these contingency tables because we learned about them in session 3 or 4, I believe, when we dealt with probability, okay? So these should look familiar to you and not be as scary because you've learned them already. So, again, just a cross tabulation of paired observations into categories, right? So you have category 1 here, category 2, so I guess in this case, variable A, variable B, right? And then you have all of your paired observations, right? So this is just the intersection, right? Think of it that way. The intersection of variable 1, or variable A and variable B, A1, B1, A2, B2, all that stuff, guys, okay? And this, again, these are your row totals and then your column totals here, all right? This is just a general form, okay? But let's get into the actual chi-square test itself, okay? We have our data in our table and we can run what's called a chi-square test, and we run it for independence, right? So we can either run a test for independence, and if we find that it's not, it's definitely homogeneous, and they can't rely on themselves. They have to rely, they're dependent basically. So again, we state these hypotheses based on this here, right? So our null hypothesis is always variable A is independent of variable B, or the alternative is variable A is not independent of variable B, okay? And a lot of times there's some examples where you'll see that variable A, they won't say directly is independent of variable B. They may say something else like does not rely on, or is not related to, or anything like that, okay? Same thing, independence, not independent, okay? All that stuff. So it's a test based on frequencies. It measures association between two variables, A and B. And this is what's called a distribution-free test because no assumptions need to be made about the shape of the population, right? So every other test that we've ever taken in terms of hypothesis tests and all that stuff, we have to assume normality for the population, right? Well, in this chi-square test, you don't have to assume normality, right? That's the great thing about this test, okay? So, our test for independence, right? So there's a Greek letter called chi, and we would just use x squared here, okay? Capital X squared, mind you, okay? And this looks real scary, I know, but it's really not bad, okay? Just because there's rows and columns, right? So RC, the sum of all the rows, the sum of all the columns, right? And all this is saying is we take the sum of our observed values minus our expected values squared. That's all over the expected value, okay? And again, degrees of freedom here, it's really easy. Rows minus 1 times columns minus 1. That's how we find our degrees of freedom. And again, we haven't talked about expected values for contingency tables yet. We're going to get into that in just a second, okay? But we'll have all of the observed values in the contingency table, subtract them by our expected value, divide it by the expected value. Important here, this is squared, okay? So it's really not that bad, I promise. It is a little tedious because there may be, it may be a 3x4 table. You have to do it, 12 times. It can be a little tedious, but it's not that bad, guys, I promise, because this is simple math. We all can subtract and square and divide, okay? So, again, if the two variables are independent, right? So if A is independent of B, then this is f of jk. So this is your observed value, right? So then your observed value it should be close to the expected value, right? Leading to a chi-square test statistic near 0, right? So the closer it is to 0, the more independent it's probably going to be, okay? Again, chi-square test can't be negative, again, because we have to square the observed minus the expected values, okay? So it can't be negative, so if it's negative, you screwed up, okay? And so since it can't be negative, it's always, always, always a right tail test, all right? Always and forever, till death do us part, okay? The test statistics far enough is far enough in the right tail, if the test statistic is far enough in the right tail, we reject the null hypothesis, okay? Simple stuff, right? We've been doing this for the last 2 sessions, okay? The test statistic is compared with the critical value, right? We've taken critical values based on alpha before, so I'm not worried that you guys don't know that, okay? And it has one parameter, again, degrees of freedom, okay? All it is a number of rows minus 1 times the number of columns minus 1, okay? Multiply those together. You can find these critical values from chi-square distribution in Appendix E. I know we have so many appendices, right? But these help you solve problems, okay? So you can find these chi-square distribution critical values in Appendix E. It's on page 771 of your textbook, okay? And it just looks something like this, right? So you have your degree of freedom, you have your, you have your alpha here, and you just kind of match it to whatever you're trying to find here, right? So if your degrees of freedom are 5 and your alpha is 0.10, that's my chi-square distribution critical value, 9.236, okay? So, expected frequency. How do I find expected frequency of a I guess in this case of our value, right? So our expected value is just our row total times our column total divided by the number, our total number in our sample, right? And this will make more sense once there's actually a table to kind of look at. I know it's confusing based on this. It's really simple, okay? But this is the formula to find your expected value, okay? So real quick, I just want to walk through an example really quick. A really simple example. It kind of helps you see it visually what the heck I'm talking about, okay? Because I know that this can kind of be a little overwhelming. We talked about a lot of material in a short amount of time, but this is the last couple of slides, guys. You can do this, I promise. So, a really simple example, right? So we have 500 elementary school boys and girls are asked which is their favorite color, blue, green, or pink. And the results are shown below, right? We have our boys here, girls here, blue, green, pink, and then they're divided up based on what their favorite color is, right? So we have our row total here, our row total here, and then our column totals, okay? And so the question is using alpha equal to 0.05. So right there's our alpha. Again, always important to write what you know down, okay? That way you can always refer back to it, okay? Would you conclude that there is a relationship between gender and favorite color? All right, so how do we do this? Where do we start? This is this is a little bit more steps than what we've talked about, but it's the same process, okay? We use these 7 steps, we'll figure our chi-square test out every time, guys, I promise. Okay, so step 1, we define the null and our alternative hypothesis, okay? Hypotheses, excuse me, it's plural. So for our null hypothesis, for the population of elementary school students, gender and favorite color are not related. Again, you're not always gonna see independent, okay? You have to figure it out. So if it says are not related, that means they're independent, right? Okay, so our alternative hypothesis would be that they are related, obviously, okay? Again, 2 mutually exclusive events. There's no overlap in them, okay? So we've defined our hypotheses. Step 2, state the alpha. Again, writing information down that you already have. We have our chart, our contingency table here. We have our alpha here. So then our step 3 is we calculate our degrees of freedom, right? Because we need those to solve for our chi-square distribution, or find our critical value in our distribution table of chi-squared, Appendix E. Okay, so number of rows, there's 2 rows here, so 2 minus 1. Number of columns, 1, 2, 3, 3 minus 1, okay? 1 times 2 is 2, simple math, right? So degrees of freedom here, 2, real simple, right? So our next step here, I know this is really blurry, I'm sorry. Again, pictures don't cooperate well in PowerPoint, okay? So we have our degrees of freedom 2 here, we have our alpha 0.05, and we go till they meet, right? And in this case, they meet at a critical value of 5.99147. Okay. So, and again, I only put it at 5.99 here. I didn't actually do 147. I just rounded it to 2 decimal places. Okay. To me, it's easier to read that way. All right. So Step 4, we always state our decision rule, right? Because we have to know how to reject or fail to reject, right? So if chi-squared is greater than 5.99, again, greater than, we always do a right tail test in chi-squared. So anytime it always has to be greater than, always greater than. We reject the null hypothesis, okay? Step 5 is we calculate our test statistic, all right? And this is the most cumbersome part of the steps for a chi-squared, okay? So we have our observed values here. The observed values are already given to us, right? Because this is our table from earlier. So the first thing we need to do is find our observed value, okay? So our observed value here is just the column total times the row total, right? So in this case, for boys, so if I wanted to find the expected value for boys whose favorite color are blue, I would take the row total, so 100, or the column total, so 120, and I would multiply it by 300, right? And then I would divide by the total sample size, n. So 120 times 300 divided by 500, you get your expected value for boys whose favorite color is blue, all right? That's literally all the expected value is, okay? That's really easy, really simple. You can find this really quickly, and it's really simple, guys. So, and this is the same step, but I just wanted to fill all the rest of these in so you could see them, right? So same thing here. I would do 180 times 300 divided by 500. And this one I would do 200 times 300 divided by 500. And I would do the same thing for these, okay? Really easy, really simple. You've just found your expected values, okay? So now comes the actual test statistic part, okay? So in order to do this, I need to take the sum of all of these, right? So I need to take the sum of the observed value minus the expected value, square it, and then divide by the expected value, okay? So in this case, I would take, and I'll put these in parentheses here just so it's kind of easier to see, right? This is my observed value, 72 in parentheses is my expected value, okay? So following this formula here, my chi-squared is equal to 100 minus 72, so 100 minus 72 squared divided by 72. And I would just do these for all six values in the table. Okay, I'm not gonna go through all of these with you, but you can see, right, they just literally plug and play. 20 minus 48 divided by 48, okay? 30 minus 72 squared divided by 72, okay? Real simple. If I follow this logic and do all this math, algebraically, it comes out to chi-squared equal to 276.389. Okay, that's what our test statistic is. And as you can see, step 6, state the results. If it's greater than 5.99, we reject the null hypothesis. I hope we can all see that 276.389 is way larger than 5.99, okay? So, in that instance, we would reject the null hypothesis, okay? So step 7, state the conclusion. In this population, we reject the null hypothesis, therefore there is a relationship between gender and favorite color. That means they are related, okay? They are not independent of each other, all right? That's all it is. Step 7, our step-by-step instructions. How do we do chi-square tests? I just showed you, okay? That was a really simple example, but you follow that for every other problem we work, and you'll be golden, and you'll understand chi-square tests like a master, okay? So, I want you guys to think about this problem. I want you guys to work it out. It's just one problem, but it's just a chi-square test. I want you to follow the steps, okay? But before you do that, I just want to say you made it to the end of the class. You're done. Congratulations, you made it. It is finished, as some would say. Sorry, that was cheesy. But anyway, next week there will be a cumulative final. So study, study, study. However, you're going to love me because I've talked with Mrs. Bernardi and we've decided that we will let you have open note, open book on the test, right? We just felt like it's an 8-week course. We're throwing a lot at you in 3 hours, and I didn't think a 3x5 note card was going to be fair enough. So we're making this as easy as possible for you. Open note, open book. I hope you guys took good notes. If not, find somebody who did, okay? And also, I have another surprise. I will be in class next week for the final, and I will help you guys review before the test. So class starts at 12. I'll be there whenever, okay? Just let Mrs. Bernardi know, and she'll let me know, and I will be there whenever you guys need me, okay? And so what I planned on doing was I'll get there early so we can review up until class time, but then I'll spend the first, since I'll be there early, I'll spend just the first 60 minutes helping you guys review some more, right? So what I want you guys to do is bring questions, okay? Figure out what you don't know, put it in a question format, and then ask me, okay? Because I can't help you if I don't know what you need help with, okay? So please come ready to ask questions, and I will be prepared, hopefully, to answer them. Last thing, you can freaking do this, okay? I believe in every one of you. You're smart. You can figure it out. And that's it. I'm really proud of you guys. Thanks for listening to me blabber on for 7 sessions, 7 weeks. I hopefully will get to teach more, and I hope you guys enjoyed having me. I enjoyed being here, and you guys have a great Christmas break and rest of your school year. See you guys later.